Alright, silly people, here's the situation. We are initiating the solving of the Kepler problem using these canonical transformations here. The u equals r plus x and v is equal to r minus x. Um, to do this, we're going to have to start with the Lagrangian, end up with the Hamiltonian, and then solve the Hamilton-Jacobi equation. Uh, so it's a pretty long problem with lots of crazy stuff happening. So Um, first, let's just write down the Lagrangian of the Kepler problem, which is given in Goldstein. I'm just going to use it here. M over 2 r dot squared plus r squared psi dot squared, where psi is just the angle of its motion, plus k over r, where k is stuff like the object's mass and stuff. Um, so we're going to have to solve for r and psi in these new variables u and v. To do this, we're going to have to actually, um, assuming that x is actually like the x position of the thing in its orbit, we can rewrite these guys as r plus r cosine psi and r minus r cosine psi, making the substitution of x equals to r cosine psi. I don't think that's too egregious. Um, and so we can just solve for r. First thing, I'm gonna say cosine psi is equal to u minus r divided by r. And plug that into this guy, so we have v is equal to r minus u minus r, which is r, it's 2r minus u, and so v plus u over 2 is equal to r. That's r taken care of. We can plug this into the cosine psi equation. We'll have u minus u plus v over 2 divided by u plus v over 2. I'll just multiply the top and bottom by 2 to get 2u minus v over u plus v, and simplify to u minus v over u plus v. So that's that. Now I need time derivatives. The r one is quite easy because you'll just have the time derivative of u plus the time derivative of v over 2. It's not too bad. The cosine psi is pretty difficult. So we're actually gonna, so we're taking the time derivative of cosine psi will equal the time derivative of u minus v, u plus v. So we'll do a partial derivative on cosine psi and multiply it by psi dot. So we'll have negative sine psi dot equals, on the right hand side it's going to be a quotient rule problem, so it's going to be u plus v, u dot minus v dot minus u minus v, u dot plus v dot over u plus v squared. So I think let's go ahead and try and simplify the right-hand side before we do anything else. Um, so on the top, it'll be u dot minus v dot plus vu dot minus v dot, and then minus all of this stuff, which is going to be u dot plus v dot minus vu dot minus v dot over u plus v squared. We are going to have some cancellation, which is lovely. The u dot will cancel out with the other u dot. We get to keep uv dot, and get to keep vu dot. Vv dot does cancel out though, so it's just the cross terms that remain. And it's going to be minus 2 uv dot plus 2 vu dot over u plus v squared. But now we have to find out what sine of psi is in terms of u and v. So we started with this thing here, u minus cosine psi equals u minus v over u plus v. We can put this in terms of sine of psi, first by squaring it. So we'll have cosine squared psi is equal to u minus v squared over u plus v squared, which I'm going to expand the top bit but not the bottom bit. So that's going to be u squared plus v squared minus 2 uv. Right. Then I'm going to subtract both sides from 1. So we're going to have 1 minus cosine squared psi is equal to 1 minus u squared plus v squared minus 2 uv, u plus v squared. And so the left-hand side will become sine squared psi. The right-hand side is tough to deal with. Quite tough to deal with. So I'm just going to leave it as it is just now. U plus v squared on the bottom. So you can just take the square root of both sides. We'll have sine psi on the right, and I'm going to actually now multiply 1 by u plus v squared over u plus v squared so that they have the same denominators, and I'm going to expand u plus v squared as well. So that's going to be u squared plus v squared plus 2uv over u plus v squared, and then minus the same stuff that we had before. Just like before, the squared terms will cancel each other out, but the cross terms will remain. So we have u squared cancels out u squared, v squared cancels out v squared. And then we'll have the square root of 4 uv over u plus v squared, um, which we can even simplify. It's going to be 2 over u plus v times the square root of uv. All right. Now I can take this and plug it back into this stuff that we had before, that equation there. So I'm just going to grab that actually. Grab this. That minus sign is actually inside of the fraction there. On the left-hand side, we had minus sign psi times psi dot. So we'll do minus 2 root uv. That's gross. Root uv over u plus v psi dot. So we'll be able to cancel out one of the powers of u plus v from the left-hand side. So that's going to be 1. Everything has a factor of 2, so we'll cancel out 2 as well. Then we'll move the minus sign over to the right, so that we have a final form of psi dot in terms of u and v, which is psi dot equals v u dot minus u v dot divided by u plus v times the square root of uv. I literally just wrote it wrong. After distributing the minus sign on that side, it's just going to be u v dot minus v u dot. Yeah. Okay. So remember this psi dot term in the Lagrangian is actually squared. So I'll need to square this whole thing. We'll have u plus v squared times uv on the bottom. And then let's just write out the whole Lagrangian then. L is equal to m over 2. We found that r dot was u dot plus v dot over 2, so the squared version of that is going to be u dot plus v dot squared over 4. And then we have u plus v over 2 squared, so it's r squared psi dot squared, so we'll have u plus v squared over 4 times uv dot minus vu dot squared over u plus v squared uv. Those u plus v squared terms will cancel out, turns out. And we'll distribute the 4 back outside of the parentheses. So it'll be m over 8. Let's go ahead and FOIL out these squared terms. U dot squared plus v dot squared minus u squared v dot squared minus v plus v squared u dot squared minus 2 u dot v dot all over uv. You can probably guess that we can simplify that a little bit more if we just multiply this left-hand term here um, by uv so that they have the same denominator. They'll have m over 8. I'll bring the uv out just to demonstrate this. It'll be um, u dot squared u plus v dot squared, or u dot squared v plus, oh shit, I forgot a term. Forgot a term right here, which is going to be 2u dot v dot. Then on the inside we'll have u dot squared u plus v dot squared v plus, actually both of these are multiplied by u and v, so u dot squared uv plus v dot squared uv minus 2, or plus 2 u dot v dot minus that stuff that we had before. That should have a minus sign on it now. This will have a plus sign on it now. 2u dot v dot. Wait. That's plus, this is plus. This is plus, this is plus, this is minus. Okay. Now we're looking cool, now we're looking great, because this will cancel out this. Uh-huh. 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 And I think that's about as simple as it gets. I'm gonna collect u dot squared terms. It'll be uv uv plus v squared. And I'll collect v dot squared terms. It'll be uv plus u squared. Yeah, and then I'm going to redistribute the 1 over uv from the outside. So it's going to be m over 8 u dot squared is going to be 1 plus v divided by u. V dot squared is going to be 1 plus u divided by v. I've been neglecting the potential term. Plus k over r, so it's going to be plus 2k v plus u. Right? Yeah, so that's about as simple as it gets, actually. It doesn't get much simpler, but now we can go ahead and get our canonical momentum so we can start constructing the Hamiltonian. So there's going to be two canonical momentum, one in the u direction, one in the v direction. So pu, which is del L del u dot, will be m over 4 u dot times 1 plus v over u. PV will be del L del v dot, which is going to be m over 4 v dot 1 plus u over v. And then we're going to put the Lagrangian in terms of the momentum first before we start making the Hamiltonian happen. We'll say that u dot is equal to 4pu over m divided by that stuff, so minus 1 there. That'll be 4pv over m times 1 plus u over v inverse. And then plugging those into the Lagrangian, m over 8. On the inside, we'll have 16pu squared over m squared 1 plus v over u to the minus 2 times 1 plus v over u to the positive 1. Similar situation over here. It's going to be 16 p v squared m squared 1 plus v over u minus 2. But that's going to be u over v actually. U over v minus 2 times 1 plus u over v plus the potential term 2k plus v. 2k over v plus u. Let's take those 16 m squareds out. Make this look a bit prettier. I'm actually going to do it down here. It'll be 2 over m. Yeah, and then that's going to be pu squared 1 plus v over u to the minus 1 plus pv 1 plus p squared 1 plus u over v minus 1. Awesome. Let's do that Hamiltonian now, which is going to be pu u dot plus pv v dot minus L, which we'll put in terms of our momentum. So that's going to be pu squared times 1 plus v over u minus 1. That's actually going to be 4 pu squared over m. Yep. And that's going to be 4 over m pv squared 1 plus u over v minus 1. All of that minus this stuff, which I'm just going to copy over. Oh, it doesn't even fit. Minus that and minus 2k over v plus u. So collecting like terms, we'll just have 2 pu squared over m 1 plus v over u minus 1 plus 2 pv squared over m 1 plus v, it's u over v minus 1 now. It's 1 minus 2k over u plus v. Now I'm going to start re-simplifying these so that we don't have inverse fraction terms. So inside of those parentheses, just going to make sure everything has the same denominators. So it's going to be u plus v over u minus 1 there. Over m, and then u, actually it's going to be v plus u over v minus 1 minus 2k over u plus v. And then actually invert it so that actually everything is over u plus v in this Hamiltonian, which is incredibly useful. I'm going to not put it in parentheses. V over u plus v minus 2k over u plus v. Now, I'm going to write the Hamilton-Jacobi equation for this, which, I mean, it's not going to be terrible. So the fact that this Hamiltonian is separable in u and v means we can write the principal function as a combination of Hamilton's characteristic functions of u and v minus some constant alpha sub 1, which will represent the energy of the system. So this is actual physics now instead of algebra. The principal function will be u sub u of u plus wv of v minus alpha 1t, where wu and wv are Hamilton's characteristic functions, which have the relationship of pu being del wu at del u, and pv will be the partial derivative of the v function with v, and alpha 1 is just the energy of the system. So exactly equal to the Hamiltonian, actually. And then when we put this in Hamilton-Jacobi equation, all we're doing is basically like we're rewriting the Hamiltonian, but in terms of these momentum transformations and setting alpha 1 on the other side. So it's going to be del wu del u squared u over u plus v plus del wv del v squared v over v plus u right there, and then minus 2k over u plus v is equal to alpha 1. That's the Hamilton-Jacobi equation. We can just go ahead and put all of those u plus v's on the other side of the equation now, so that we'll have 2u over m del wu del u squared plus del wv del v squared times 2v over m minus 2k is equal to u alpha 1 plus v alpha 1. Go ahead and distribute that multiplication. So that means that this can be split up into two separate integrals to solve the problem. That 2k, we're just going to split up into two different factors of k. And so by doing this, we'll be able to obtain constants of u and v, which will represent their constant momentum in those directions. So just taking half of this function, the stuff that is dependent on u, del u squared minus k minus alpha 1u, will have it be called alpha u squared, which we can then solve this. We'll have del wu over del u is equal to alpha u squared plus, go ahead and multiply that stuff, m over 2u minus alpha u, that's times alpha u squared, plus m over 2u k plus m over 2 alpha 1, all under a square root. That is an integral that could be solved, but all the problem asks for us to do is to reduce the problem to quadratures, so it's not really necessary to solve the integral at this point. You can do the same thing for v, just stealing half of the Hamilton-Jacobi equation, just the stuff that involves v, so 2v over m, we'll have del wv, del v squared minus k minus alpha 1 v equals alpha v squared. And then it's just solving for that stuff again. So del wv, del v equals m over 2v alpha v squared minus or plus 2v m over 2v k plus m over 2 alpha 1, that factor again. So these equations have been reduced to quadratures, which means you can solve those integrals if you wish. I'm not going to, because that looks evil.